Hello and thank you for coming to our colloquium. I'm delighted to introduce our speaker today, Matan Ben Sion from Radboud University of Nijmegen in Netherlands. Matan started his scientific education as a chemist, but fortunately converted fast into physics, and since his master's and PhD he did at the group of Paul Chaikin at NYU with Ned Zeman. Then he was a postdoc at ESPCI with Olivier Dauchot, and also a postdoc with Lahini. What's his first name? Yoav Lahini, yeah, at Tel Aviv University. So since 2023, Matanya is at the Radboud University in the Netherlands, and at that point I would like to thank Matanya for coming here. It's a long way, and the stage is yours.
Thank you very much. Thanks for the introduction. As Eli said, today I'm in the Donders Institute, which is the Center for Cognition, and there I'm in the Department of Artificial Intelligence, which might strike you as a bit surprising, me coming from physics, but one of the things we're doing there in my little group is we're trying to understand how can we make something that looks like intelligence, looks like something that's cognitive, but that is very atomistic, very mechanical, actually like a chemist, like, oh, can a bunch of molecules come together and make something greater? So in a way, I'm a chemist that does swarm robotics. Now, why am I interested in swarms? I'll say that in a second, but the talk is about robot uprising. We'll show that. And also Rise of the Dead. I promise I'll also show that. And a few lessons that we had from looking at very, very simple systems in active matter, and how we got some insight about biological systems, and maybe some insight for engineering. Why am I interested in swarms? Because they're everywhere. On every length scale. On the meter scale, you can have here a herd of sheep that is going through a constriction. If you zoom in on this patch of soil, you can see a swarm of worms. And you can maybe further zoom in and say, oh, maybe this little worm is infested. And here you see a colony of bacteria. And despite spanning many orders of magnitude in length scale, you see this structural similarity here. It seems a little bit like the structures that we see in materials.
Is there bacteria inside these worms?
No, this is heuristically. This is not really this.
And the worms are not inside the sheep.
No, but there are. Whoever has little kids, okay. Sometimes swarms are looked at as material, and this is sort of the idea that I'm trying to parade. As materials, we can associate them with material properties or states, like something very dilute, like a gas with its sperm cells, or a solid in cellular tissue with its Dracula fruit fly, wing of the fruit fly, or a liquid that can be polar, like a school of fish pointing all in the same direction, or pneumatic, like again a bacteria that can be apolar and can move forward and backwards. But, and this is why I'm in the physics department, but unlike materials, unlike typical materials, these materials are far from equilibrium. They break time reversal symmetry, they break Galilean invariance, they break all these symmetries, they make them very different and give us more opportunities for asking more questions and making new things. Moreover, I should say that whenever you look at artificial swarms, we're nowhere near what we see in nature. And this really tells us there are some underlying principles that we're not really understanding yet. One way of understanding them is looking at them, diving with fish, if you like that, or looking at birds, or maybe having a really nice microscope and imaging some bacteria using confocal. Another way is making them. And by really making them, maybe you can get some insight sometimes. And this is sort of the approach that I'm taking, what I call extreme experimental reductionism. I design artificial systems bottom up and see how they make greater structure or greater function. These are a few examples. I just want to give you some idea of the things that we break in the process. This is self-assembly of a chiral structure that is forming a tetrahedron that is left-handed, and you can also make a right-handed. Here you have particles that are on the micron scale. You see here the scale bar. What drives them is fluctuations, thermal fluctuations. What binds them is potentials, molecular attraction. And you can form structures, something on this range of a micron scale, free-form structures on this micron scale using only thermal diffusion. It allows things to diffuse enough. But if you want to make something bigger, things have to be active, because diffusing 1 micron a second is nice when you're the micro. But if you're a millimeter-sized particle, it would take you 25 years to diffuse your own size in water under thermal fluctuations. So you need to drive. You need to have a drive. This is another example of artificial microswimmers. They swim. They may look like bacteria, but they start as vials on the tube. And I think I presented them last time I was here, almost 2 years ago. What you see here is a form of coexistence of a dilute phase, gas-like phase, with a dense phase, liquid-like phase, and a dynamical steady state, the particles coming in and out. And this comes about not from molecular attraction, but from activity, from the fact that they slow down as they have higher concentration, but they still have fluctuations. Here, on the micron scale, there is activity, there is drive, there is power at every one of these constituents. But if you want to make something like a swarm that is adaptive, that can learn, just being active is not enough. You also want to have information fluctuations. Individuals have to somehow learn from their environment or learn from one another. And this is the last example that I'm showing here of a swarm that learns how to phototaxis together. At first, they're not really good, but well, there's light all of a sudden. But then they learn from one another through their past. Formally, it's known as reinforcement learning, but it's a decentralized reinforcement learning. Again, I'm thinking about them as atoms. There is no global information. Eventually they converge, and we show why they can converge and when can they converge collectively. So I don't want to spend too much time on this. I want to talk about cooperative effect that we actually saw in microscopic objects. But before this, a couple examples of what we see in engineering. So this is something like a swarm. Sometimes people will call it a swarm. These are digital fireworks. It's made out of drones that only shine light. And there are a few hundreds of them here. And one of the reasons I don't see them as a swarm, and it's still very different from natural swarms, is that there is a tower that controls all of them. So the system is not scalable, right? If you want to make 1,000 or 10,000 of them, you need a stronger tower or a different robot. So it doesn't scale the same way we like to think about natural systems or atoms. Another really nice example of swarm, which is in principle more scalable, is this work from Rubinstein and Nagpal from a decade ago, of how 1,000 robots can collectively assemble into a star without any external information. Nothing guides them externally. They do this through interaction with one another. There are a few caveats here, though. One is that they all have to go through this origin and sort of zero themselves so they can know where they are. Another one is that they're very slow. This thing is sped up. It's 11 hours. You don't have to take my word for this. Take the leading author's word. Watching the experiment run is like watching paint dry. And this sounds frustrating, but it's actually a feature here. It's a feature because this way they don't collide. Collisions will introduce noise. Noise will completely ruin the whole premise of how this thing can work. And they actually say this in their work, that we need to find a system that is adaptive to noise or can sustain noise. And this is what we think about usually when we think about active particles, or in statistical physics. Actually, there are stochastic agents. So let's, so a small summary: artificial swarms are nowhere near as agile as natural swarms, and it suggests we don't understand something profound. So in order to understand, we need to make things more simple. So here's a quote from Brian Keringan. Does anyone know this guy? Thank you. The C programming language. Wow, it feels like I'm talking about punch cards at this point. It was an important book at the time. And he says that debugging is twice as hard as writing the code in the first place. So if you are as clever as you are when you're writing the code, you will never be able to debug it. So if you want to write something, make it really, really simple. Otherwise, you won't be able to figure out how to fix it. And more in the context of swarms and robotics, quote from an old work by Ren Brooks and Anita Flynn. This was the title of the paper that later turned into a movie, is let's make robots fast, cheap, and out of control. So they can scale. And then they were thinking about taking over the solar system, preceding some of today's entrepreneurs. Okay, let's start breaking down our agents. This is an example from Feinerman's group and from Weizmann. These are a bunch of ants doing cooperative transport. Each ant has an ability to compute. It has a CPU. It has memory. It has sensors. And what can you do? It also has to follow laws of nature, right? F equals ma on this scale. And the question is, can you make something this nice, this sophisticated with only F equals ma, only mechanics? And this is sort of what I'm always asking myself. When do atoms, F equals ma, start to swarm? Where do you go from an atom, a molecule, to a swarm? Where do you draw the line? What symmetries do you break? What do you need to build into this? A nice work that I really recommend everyone who does statistical mechanics is to read, even just the beginning of it, is the work by Salone, Kafri, also from Technion, Kada, and Tayur. That pressure is not a state function in generic active fluid, which is a very oddly phrased title. It's a negating title. Actually, the surprise is that if you have a system that is active, that breaks time reversal symmetry on the individual, you can have pressure being a state function. But they show that it's not always the case, and generically it's not the case. And the reason I recommend reading this is because once I read this book, this paper, I realized what is pressure. There is this magic that happens with pressure, that mechanical pressure, F over ma, is the same as thermodynamic pressure. And they show why this and when this can break in an active system, and specifically it breaks when the particles, and here I'm writing a few equations, Langevin-like equations. So this is the velocity of a particle in the overdamped limit. This is the force acting on it, and this is its mobility, but it has a self-propulsion. So this is where the brakes are Galilean invariance, and always likes to move in the direction of its heading E, and its heading is, I'm not defining it here. Oh yeah, it's here. It's this angle between the orientation and the x-axis. The heading undergoes Brownian motion. This is a stochastic noise here. So it actually goes in a straight line, but then its heading diffuses around, and on short time it looks like it's ballistic, straight. If you like polymer physics, it's persistent. On longer times, it looks diffusive, has a persistent line. But if there is a coupling between the orientation and the velocity or the position, this relation is no longer generally true. And generically, you will always have some coupling like this. The example of the coupling they give in the paper is of an oblate object. So whenever you push on it, it will turn. So let's look when there is strong coupling. Maybe there is where we're going to start breaking atoms, atomistic description, and start moving more towards swarms. Questions?
What is F? What is the free energy here?
This is not. It's not free energy. It's a torque term.
No, in the second.
No. Inequality. When you wrote the inequality, there's of course.
Oh, I mean
The fancy
Curly F.
Curly F,
Yeah.
Yes.
F. So this is. It's not in the. It's not. You can write it. Well, here for this system, you can find what is the F. It will have to do.
How can you find? I mean, F is defined in thermal equilibrium by some partition function.
Mm-hmm.
F is log of the partition function in general.
Mm-hmm.
And then you have to define a temperature, but you don't have a temperature, so I don't understand what is this F.
If you really want to get this, you have to read that paper. But what they show is that the F, this free energy, that everything else will be derivatives of, is dependent on the concentration, on all these intrinsic properties that we're usually thinking about when we're thinking about equilibrium physics.
So they define it somehow.
Mm-hmm.
That's why it doesn't work.
Yes,
Yeah.
exactly.
You find something and then it doesn't work.
I mean, in general, you cannot write
It's defined for a very restricted. It's defined for a very restricted case.
So if something doesn't work, the question is it surprising?
No, the thing is, it's surprising that it sometimes works. This is surprising. The reason that it's not working is that this term, and I will get to this in the rest of the talk. This term is actually very weird, and you should always expect to have some coupling. There is no symmetry that really forbids it, and the cases where it is, you don't have this from symmetry is actually very peculiar. So you always have some coupling like this, and you will always break this generic picture.
That's fine. Then you'd never have a thermodynamic equilibrium.
True. True. You won't. Well, it's not thermodynamic equilibrium. You won't be able to define pressure as a state function.
Everything. No temperature, no efficient function, no nothing.
Okay, where this is your examples of this, it's actually useful, this idea. So if we think about, this is a cartoon of bacteria. If we think about bacteria as a gas, just as a PV and KT gas, and you put some of the bacteria on one side of this chamber, and it has little pores. You expect that after some time it will equilibrate and you have the same number of particles on both sides. So this is like they did this experiment. So this is a bunch of wedges. They look like this. So there's actually an opening here, and after like half an hour or an hour and a half, they find proliferation of bacteria on one side. So this is an example where something that you don't expect in thermodynamic systems, where things move to the side. And now we sort of understand this better because the bacteria it's elongated. It has a torque once it's aligning or colliding with these walls, and then they're all moving to one side. Why is this useful? It means that you can make a passive device that will get rid of bacteria. Right? So you can get rid of contamination with just wedges, just by getting this idea of, oh, the system is not in equilibrium, you can use it. There are actually many examples of such idea of things that are aligning with an external force. So the bacteria, once it's being pushed, it's turning. One which is very famous is the Vichik model, which sort of established the flocking transition once particles are aligning with one another, like active particles are aligning with one another, like spins that align with one another as a form of the dynamical phase transition. And then there's a whole industry of work that preceded that and looked at different ways of how particles that align, different aligning strengths, different aligning interactions, different graphs of alignment, and so on. If you look more before this work, you actually find that there were signs of this that preceded that, one by Reynolds in Computer Graphics journal that suggested an alignment of particles as a way of creating computer graphics that doesn't require you to orchestrate each and every one of the particles, and then you can make herds, like you say you have in the Lion Kings. I don't know what's the right reference these days. Many things that go together, you don't have to control each and every one of them. You just create a rule. And I found another work that even preceded that by Koi in the Japanese Social Scientific Societies of Fisheries, where they said, oh, actually fish also aligns, and they all write the similar equations for alignment. So two particles approach each other, and there's some phenomenological term that makes them align with one another. So alignment is important. If you want to jump from atoms to swarms, something with alignment has to happen. So let's try and design robots that make some sort of alignment. Not sure what's the symmetry that we'll have to break in their design, but we'll see in a second. So this is the robot that we made, very simple. Well, it's the beginning of the robot. This is the drive, the battery, a switch, and two vibration motors. The rotating in opposite directions, so there's no net torque. And then this is what it looks like. Just break. You can also hear it. Okay, it doesn't really go anywhere, so we couple it to something mechanical. These are these elastic legs. We model them as using Euler-Bernoulli thin beam. Same equation used for bridges or nanotubes. And you can sort of match this noise, the frequency of the motors that will be near resonance with the beams, make them soft enough, and do some tuning of their design to come up with this beautiful machine that is this very simple stochastic robot that basically goes barely in a straight line. Okay, so we have this stochastic robot, stochastic active particle. It sort of confers to these equations. You can sort of see that it has self-propulsion speed. It has some nominal forward motion. It's very noisy. This is a noise term for the orientation. And we can measure these things. Okay, we can see how they behave. We also found that we can take this idea and put this in the kilobots that I showed earlier. That was very slow. This is real time of these kilobots. What I showed earlier. This is with this structure. It's a little faster. It's 10 times faster. And this is sort of was a nice example of how taking some very simple mechanical design and putting it on something that a computer scientist built to make something more robust. This is important when you want to do a swarm, because swarms need to converge on a large scale, on a large number scale. You want things to move fast enough before the battery runs out.
Is it still overdamped?
Excellent question. Beautiful question. I'll get to that. I'll get to that in a second. I'll just tease and say that these equations are phenomenological. Okay, there is no a priori reason to show why is there mobility here, right? These are inertial quantities. It's not Stokes flow. Why am I writing mu? I'll get to that.
What are the source of the theta, of the noise into that changes theta?
These motors are asynchronous. They vibrate not in sync, so they're very noisy. One time it will vibrate more to the right, another time a little more to the left. It's not a thermal noise, if this is what you're after. There's also little defects in the ground. So it's, well, in one word, it's reality.
F is a constant force, it's fixed in time.
For now, yes. I haven't shown it. This is a perfect question. So, okay, so we can measure the mobility, or sorry, the self-propulsion. We can measure maybe the noise, and we can measure the mobility. I'll show you that in a second. So this is the nominal speed. You measure the mean square displacement in the ballistic regime, where it's persistent, and it just proportional to quadratic of time, and you get it's 5 centimeters a second, you get some number. And then how do you measure the mobility? This is your question. You apply an external force. So I said, okay, how do you apply an external force? Let's use the force that we always have. Gravity, yes, we all know this this drawing. Let's just put it on a tilted plane. I can control the tilt, get a control force. I can measure what's the whatever angle of repose or what's the sliding speed, etc. Just measure how quickly does it go down. From this I can get the mobility. So I put it on a tilted plate. Well, this is again the same experiment, but now I tilt the plate. And the idea is just you can extract the mobility from how quickly does it go down. But it didn't go down. It went up. And I thought this is weird. I put it on the other side. No, it persistently goes up. And I remember showing this to Olivier Deschamps, and he said, "C'est pas possible." He was looking at it. It was like in front of him. He was like, "This is impossible." He had a good reason to say this is impossible, and this is where we started learning new things. When you think about the work of particles that align with one another, the way the alignment, this torque term, is usually depicted as this has some orientation, this has another orientation, and then there's some alignment rate that couples them. And then they flock together. So this is a phenomenological equation that was written. So if the orientation, the heading, and the velocity are not aligned, so if I'm moving like this, I will turn. And then there's some damping, a rate. And in order for something to turn against an external force, one of these have to be negative. It means that we don't understand something. So we looked at a slow-mo version of these experiments. This is this robot. And you can see that the front softer legs and the rear stiff leg act very differently. You can see that from the reflection, they are much more sort of skidding versus the rear leg is jumping very high. And then we took a $200,000 camera to basically get the same idea, the same result. You see that this is jumping very high, so it's not touching as much as the front legs that are doing more of a skidding motion or jumping very short. They spend very little time in the air. And this sort of microscopic picture allowed us to establish a coarse graining of this first fast dynamics, from which we reproduced all the phenomenology, but now we will have the phenomenological parameters from their microscopic origin. So this is what it looks like. You start with a particle. This is going to be our active particle. It's on the ground. This is its center of mass. This is going to be very high school level. And we're going to assume static friction, so no sliding. And whenever it hits the ground, it loses all its momentum. So complete damping once it's landing. Once it's on the ground, there's an external force, but there's also friction. So F equals ma is 0. This is the force. So this is top view. It sort of acts into the board in this case. And then you jump. Once you're in the air, no friction. There's an external force. You will accelerate under the external force, but you're jumping forward. Okay, so your motion will be a combination of the two. F now equals ma, and this is what your acceleration will look like. And your net displacement will be a combination of the two. And you spend some time in the air. And then you land, you lose all your momentum, and this whole process happens over some duration, and your aerial time is whatever, and from this you get a net displacement. And once you do the averaging, I'm not going to show the whole vector calculus, but once you do the averaging, you recover these effective equations. This effective equation. This is not very different from Drude model, where you have a mobility term for electrons that constantly lose their momentum by colliding. But you have another term for this activity, for the self-propulsion, and now the mobility that we have, we see how it comes about it comes about from the fact you're in the air. It's quadratic with the time you're in there because you're accelerating, and it also decreases with your mass because an external force will not be as effective when you're more massive. And this is sort of where this mobility is a bit funny, because usually mobility is from a viscous force, which doesn't care about inertial properties, it cares about viscosity. So these effective parameters will care about inertial properties despite having overdamped structure.
What is T?
Which one? The big T?
Big T.
It's the duration of this whole process. Now I should say that I don't care if this happens in sequence or it jumps many times, or I just care about the average T, average tau A, and so on. Just the average properties. This is the idea of this dynamical coarse graining.
Wait, but what is F now? If it, when you move on an inclined plane, you somehow care about the plane, but the moment you leave the plane, I mean, you are in the air, so F is just down, right? So why is it?
So here I'm casting everything into 2D. The inclined plane is a way of inducing a force which is in plane. And the normal force is being left implicit here by this time that you're in the air.
So it's not really relevant to the previous, to the inclined plane problem.
It's in the inclined plane. We say, I'm looking at the inclined plane and I don't care that it's inclined, I care that the fact that there's a force acting along the plane. Okay? I'm sort of brushing the fact that there is friction also. There's no friction term here. They're just breaking this down into these phases. Now,
Question? Doesn't tau A and capital T scale the same? Or proportional to each other?
depends on the drive, depends on the elasticity of the soft legs, depends on all these specific parameters. You can tune them. You can tune them. You can play with them. We actually do play with that.
So where does the angle of the tilt of the plane?
Okay, so the thing is that once you're jumping, you're not landing equally on both legs. As I showed you from the experiment, it spends more time in one of the legs. There is no sliding, but it can still pivot. And now it will create a torque. Super important ingredient. Now this force has a lever arm that has to do with the displacement of the center of mass from your pivot axis. And you will turn, and then this whole cycle will have a displacement and a rotation. Once you do the averaging for this, you recover this, what was previously a phenomenological equation for the orientation. dE dt equals E cross V cross E. But now you have the microscopic coefficient. It's kappa. And it has units of curvature. It tells you how much do you curve by an external force. There's a nice review that discusses many systems that sort of follow this equation, and here we have this for a granular dry friction system that is dominated by inertial properties that also follows something that looks like an overdamped dynamics with alignment. We know what this kappa is. It's this relation of the pivot time over the tau, the aerial time. It's times the mass over the moment of inertia. Because this torque will create the inertial rotation, and its sign and also magnitude is controlled by this delta, this shift of the center of mass relative to the pivot axis along the orientation, and delta is signed. And this will gives you negative alignment. This is how you can go against an external force. This is an example in the point mass limit. Assuming that all the mass is concentrated at this point, this kappa goes like 1 over delta. So it's sort of an intrinsic curvature-like property that these particles have. Once we figure this out, we can design robots that have positive or negative kappa. This you see, goes down, but it also turns down. So it aligns with an external force. This goes up, as I showed before. This is for the constant force. I think you asked this. Once you put constant force in these equations, you get the equation for a simple overdamped pendulum. And its stability, where it's 0 or pi, is controlled by the sign of kappa. And you can solve this, and the motion, the orientation follows these equations pretty well. And you can also calculate what is this kappa of a given design. This shouldn't come too much as a surprise. This is already known in hydrodynamical systems like missiles, sailboats, fish, and also sperm or microscopic organisms. An external shear or stress will cause you to rotate, and your stability is controlled by the interplay of the center of pressure or stresses and center of mass. This is what allows a missile or a sailboat to be stable in wherever direction it's going. Here we show this for a frictional system. It's a little bit like an electric charge. So just to build some intuition, I'll say this very quickly. So this is from Marie Sklodowska-Curie dissertation. These are alpha, beta, and gamma particles, and you see that they curve under an external magnetic force field in positive or negative direction, or just go straight, which is somewhat analogous to these equations. It's a little different, but if the force is perpendicular to the velocity, so the orientation, then it goes back exactly into the same equation, just with this kappa term being positive, negative, or zero. And the reason I'm showing this, I show this because she worked in the same lab down the street down the hall from where I was in Paris, in HPCI. Something nice about their baguettes. We gave a name for this quantity. We call it curvity because it comes from curvature, and it has units of curvature, and it comes from the particle's activity. And just to showcase this, we made robots of different sizes and showed that this actually scales with the size too. This is a bigger robot. It also turns up. It's basically the same mechanism. Center of mass is behind the center of rotation, and also goes to the opposite direction. We can also use this for sort of control, dynamical control. This is when the force is not constant. This is a robot that goes on this tilting plane. Whenever it gets to the bottom, it turns up over and over again. Again, there's no sensor here, no external supervision. It's just intrinsic. Which brings us back to the ants. In their paper, they have this statement that really caught my attention: the physiological mechanism that allows ants to push, to sense they're pushing, is still unknown. They have to respond really fast when you think about it, because an ant that pushes from this side transmits force and a speed of sound to this side, and this one has to react quickly enough. So it's not clear what the physiological mechanism, and I went to Ofer and asked him, could there be some mechanical component there? And I showed him the robots that go up, and he said that ants also tend to go up. And he took an ant, being Ofer, like this, from his leg, really, put it on a sheet of paper, like that, and the ant went up, he turned it, it went up, he turned it, it went up. So I said, oh, this is funny. So maybe it's more general than just the robots. And this spiked this collaboration, taking ants, live ants, and putting them on these tilted planes. Now we can control the force. It's alive, so we have to do a lot of averaging. But one of the things that we see is that their tendency to turn increases with the slope, which is what you have from the equations. But then we can look at their full structure using a micro CT and really slice their center of mass and moment of inertia. But if it works from ants, why not other things? So I started scouting other animals, and I came across this beautiful Vildachaya, the locust, who happens to be working with Amir Ayali in collaboration. Ayali works in Tel Aviv University. He's a world expert on locust behavior. And he said that locust also goes up. It's called negative geotaxis. Geo, Earth, taxis, go, negative, away. Goes away from Earth. It's described as a behavior. I asked him, could it be also that it has some mechanical component? And he said, okay, sure. How can you prove it's not cognitive? Why is it not deciding to do this?
You remove the brain.
So you know the joke with the fly, right? So I don't have to go through it again here. Unfortunately, I'm not a surgeon, let alone not a insect surgeon. But what we end up doing is taking a dead locust. So it's close enough. This is a dead locust on a vibrating plate, flat. You see it moves forward, so its mechanical structure already is supporting forward motion. Sort of makes sense. This is a dead locust on a tilted plate. Okay, and I'm vibrating the plate slowly. At first, it's very small, and I'm constantly slowly increasing the vibration amplitude. And notice that the first thing that it does is turn up. This equation has only one component, so immediately when there's activity, it will turn up. As I increase the amplitude, effectively increasing its nominal speed, it's strong enough to overcome this lateral force. So this equation has two components, and it can climb. And there you have it, rise of the dead. I told you this will happen, right? Of course, this is not how locusts walk. So we designed a system to measure more systematically their gait. And now we're working more deep into that and doing more finer analysis. So we use frustrate tone and lateral flexion. This is a locust that walk on a plate, and you see these little dots here. This is where its legs are contacting the surface. I can tell you more about the system later, and we're using some commercial industry standard DLC to measure how it's walking. You can see the colors represent the intensity. We already see that we can sort of predict where it's going to turn. But this gives us the microscopic properties of where exactly it's contacting, what's the pivot axis relative to the center of mass, to compare it with our model. Say, oh, maybe there is a strong mechanical component for this behavior. And if it's true with locusts and with ants, it may be true with everything.
Wouldn't it have been simpler just to put a weight and change the center of mass?
Yes, yes. You can try it with yourself. If I know that when I put the weight on myself, I behave a little differently. We tried it with the ants, overfeeding them, getting their belly very large. We tried putting some magnetic dust on them and applying forces on them. So we're doing all these little tricks. I really like when it's very sort of natural, either alive and happy or completely dead. Okay, so we have these examples that span many orders of magnitude, living and synthetic systems. Now, coming from material science and physics of materials, I thought this is actually a very weird system that once you push on it, it turns against you. So they're antagonistic, a little bit like myself. Maybe it will be, you will see something that looks like shear thickening, right? You'll take a passive particle, push it against these active particles that tend to turn against an external force, and you'll get a super linear non-Newtonian response that will resist it. So shear thickening in an active system, maybe even in a gas. So this is sort of a weird thing. Usually shear thickening is a very thick system, right? You have 50% cornstarch in this. We've got something much more interesting. So these are simulations. This is active particles that follow these set of equations. This is positive curvity. This is a passive tracer. It moves sort of Brownianly. It has something that looks like Brownian motion. This is a zero curvity in the field that's known as active Brownian particle, so no alignment with an external force. This is what you'll have in thermodynamic equilibrium also. And this is negative curvity. They start pushing it. You start getting something that looks like cooperative transport. And me being an experimentalist, I thought this is numerical Hawks. We did something more systematic. We increased the size of the passive payload. This is A over B, the passive particle, radius of the passive versus the radius of the active. See, there's some threshold. There's a jump. And I said, okay, if this is true, it should also happen in experiment. And these are experiments with positive curvity, passive payload, sort of moves around, they're getting deflected by it. Negative curvity, there's some form of spontaneous symmetry breaking, and transports all the way to the end of the system. You can measure the mean square displacement. It looks very different, much faster, much more ballistic. This is interesting. It starts to look a little bit like the ants, and this is particularly surprising. Let's look at them at this here. See, symmetry breaking and then just transports. And this is particularly surprising because the systems are very different. Also the size also controlled the same way in experiment, right? This is small particle, small payloads, diffusive motion, but positive curvity. Sorry, negative curvity, small payloads, sort of diffusive motion, some threshold, boom, release. Now, why am I saying this is weird? Because these systems are very different from one another. Right? One of them is overdamped The simulation is overdamped, strictly two-dimensional. Noise is strictly Gaussian. Experiments are with sort of quasi-two-dimensional, inertial in principle. The noise is not Gaussian, it's whatever, some colored noise, and yet you have so many quantitative lines of similarity here. Another weird property here that we found is that the transport is really cooperative. This is the trajectory of the payload, nearly straight, very ballistic. This is the trajectory of the active particle. It's much more diffusive relatively, so it's more persistent than the particles that are pushing it. You can measure it also from the mean square displacement. The payload is, again, quadratic. The active particle is initially quadratic, and then it bends over to the diffusive regime. And another really important sign of cooperativeness is that it increases superlinearly with the number of particles. So bigger swarm make the passive payload, this is LP, the persistent of the payload, more persistent. So there's some additive synergetic effect here. Let's put everything on a single figure. So this is color is simulation. See, this is where it's high speed for the passive payload. Blue is low speed. N is the exponent for the mean square displacement at the intermediate times. And you see that the active particle, the passive payload is very ballistic in this region. Negative curvature, large enough payload, much more diffusive or slower in this region. And the thing that sort of separates these two phases is this line, where kappa, the curvature, times A, the radius of the payload, equals -1.
What creates this structure in the green regime?
The features, poor averaging on my side. I should have had more simulations here to make it flat. But this is not some spectroscopic. I wouldn't read too much into it. I think this is a slightly older simulation. Now we see that it's very flat, and also you see this increase in the speed or the persistent length.
Shouldn't the payload changes its direction through time?
It does.
For long enough time?
Yeah. So
So
this
it
is what we
wouldn't
call
be ballistic
indefinitely.
forever.
Yeah. Nothing is.
Yeah.
We have. Sorry, I'm going to take 2 more minutes because we can explain this. We have a model that really captures this, I think, really nicely. We take these equations, and now the force for the payload, we model it as a radially symmetric repulsive force. So it pushes against you, but now it's not a constant force. It's something that is radial. Push it outwards, and we normalize it this way, and you have this gamma that is the profile of the force. So gamma at the rate, what we define gamma equals 1 is where the radius of the payload is at the radius of the payload. And then you do some math, then you get this dynamical system that looks, again, a little bit like this overdamped simple pendulum. Psi dot equals to sine psi. Psi is the relative angle of the orientation relative to the payload, because you have rotational symmetry, so you only care about the relative orientation, times some prefactor. This prefactor, as you see, comes from the polar symmetry of the system, and this prefactor's sign controls the stability of an active particle pushing against the payload. Let's see how. These are phase portrait. This is a phase portrait. I'm starting drawing it for an active Brownian particle. Kappa is 0. This is the radius normalized by the radius of the passive particle, and this is the relative orientation. And you see there's a fixed point at r equals a. But it's an unstable fixed point because if the particle turns away, it just goes to infinity. But if I start tuning this kappa a, so let's say I'm increasing the radius, you see it doesn't really change qualitatively this picture. But once I decrease it and I make it negative, but not just negative, but sufficiently negative, there is a local topological change in this phase portrait. There are 2 more fixed points that are being formed. You have a subcritical pitchfork bifurcation. This turns into a stable fixed point. See, everything is pointing inwards. And you have something that looks like an effective attraction for an active particle to a repulsive potential. This happens exactly at kappa a equals -1. This transition, this bifurcation, and this explains why this line where is this line coming from? So we have a geometrical condition for cooperative transport, which is nice. It really simplifies things. It looks like something like an effective attraction. And we'll also measure this by the number of particles that are against the payload. And if you think about it for a second, this condition kappa, it's kappa, or curvature plus the curvature of the payload. This is the sum of two curvatures. It looks a little bit like stability in fluid systems. Okay, where are we going with this? So conclusion one, we start with building simple robots, and we got insight into biomechanics. Conclusion two is we start with a hint from non-equilibrium statistical mechanics. You need alignment into designing swarms that do something. This is very non-trivial. If you look at swarm literature, engineers of swarms, to get something like cooperative transport, what they do is they put all the robots on one side, and then they let it push. And it sounds ridiculous, but this is sort of the only way they were able to do this. We're having some external cue, but not as an emergent spontaneous symmetry breaking system. And we're at the dawn of swarms. We're making more and more robots, yeah, this is very exciting times to make more of them. If you have questions, I'll be happy to answer. If you want to take a look at this paper, it's here. And yeah, thanks.
Yes, please. Yeah, I had two questions. One was regarding what is the point? Which number of swarm particles, robots, whatever you call them, do you go beyond what you can easily compute? And because for all of these particles, you can do the simulations rather easily. So I'm wondering, like, where is the transition point? And the second question is, have you considered looking at particles where robots where everything is not symmetrical? Maybe the particles or robots are a bit different from one side to the other.
Chiral.
Either chiral or just
left.
every robot is different.
Oh yeah, heterogeneous.
Yeah.
So I do that. They call that experiments. They're never the same. And once you see something in experiment, you know you have all these natural symmetries that are broken, and if something is robust enough for them, then you have that. I'm not sure I fully understood your first question. What's the point of simulating it, or what's...
No. At what point, if there is such a point, do you go beyond? What system size beyond which it's no longer easy to simulate?
How many particles?
We've been doing simulations in this simulations you can go in the tens of thousands, I think, or hundreds of thousands too. But this might be a question, I think, okay, maybe if I understand, so I know that in condensed matter many times, we say I want to simulate a bigger and bigger system to get to the thermodynamic limit, because that's what we have experimentally. We have a mole of Avogadro number of electrons. This is not the case with swarms. In the swarms case, to get a large enough N, you have to work really hard in finding a large enough flock or a school or build a lot of robots.
The question is more at which point does it become important to do the experiments and you cannot simply do the simulation?
I just showed you, no one thought it was going to turn against the force. I will say it 1.
Okay.
So for the transition to activity, so there have been works from the group of Joanny and Ilian, mainly showing that you don't need any activity at all to have a transition from purely passive system to active system. The only thing that you need are differences in diffusivity, and then you have this transition. So maybe you can comment on that, how it's related to your work, because you have active ingredients to show this.
Yes, I can comment on this. There's another work that we have right now that looks at that. So I think, correct me if I'm wrong, but I think you can get what you're saying into what is known as active model B. Are you familiar with this term? It's not exactly that? No. So what is that? What is that?
So it's AMPIC is transition. Maybe it's
this is the transition.
Yes.
Anyways, but one, I think something that is really, really key here is this threshold that was not known before, below which you get a really different behavior. When we're simulating at this point particles, large number of particles.
By threshold, you mean different behavior, active FPS over
I,
time?
I've made a little jump here. So there's another size in the system, which is the robot size or the active particle size. It's called B. This kappa B is also a condition for attraction because previously you had the payload A to be really big, and an active particle will allow and get attracted to it. But if the kappa or this curvature is really negative, it will also get attracted to one another, or a cluster of them. And what we see is that once the kappa B is sufficiently negative, the simple active systems, the more classical active model systems that you can say, oh, it's just a different diffusivity, are no longer the case. So one of the things that we get is size-controlled clusters, which is I don't see how you can get with different diffusivity. And the size is sort of encrypted inside this curvature, the intrinsic curvature of the particles. Let's talk about more. Yes.
I have a question sort of related to what Hanan asked. Is there some scaling with the number of particles in terms of, universality of the phenomenon?
Open question. Yeah, this is the kind of question that I'm asking now. So yeah, I have one student that looks at these kind of questions, and also, yeah, this is sort of the kind of questions that we're asking. More better characterize this transition. Is it a phase transition? I don't know if it's a phase transition. It has all sorts of signs and smell, but I don't know if it's a phase transition. And then we can go further into that.
Can you make them learn by adapting their curvature with time? Like if they manage to catch this particle, then maybe kappa evolves, and then they do some learning.
So in this. Yeah, so, yes, yeah. So, let me say something that we did, and just a simulation for now, and then sort of more general things you're suggesting. We said we can use this as a form of a control of a swarm paradigm, right? So what I told earlier, so if you have a negative enough kappa, particles get attracted to one another, they cluster, so you can get particles to cluster even when they're very dilute. A la MIPS, but it's different than MIPS. You see that there is a phase transition, a phase diagram that is different, a phase boundary and phase diagram that is different than MIPS. So they aggregate, and then they say, okay, now let's switch our kappa, and then they flock. So you get flocking, a very dilute overall concentration by making the system adaptive. In this experiment, we did sort of a more advanced version. We had robots that had a genome of 1 bit that tells them sort of what's the threshold for stopping in light, and then they learn this genome from one another, and then it's more of an adaptive system, but still not coupled to the dynamical transition we see. The question is, can we start coupling this to get them an even more richer behavior?
Asaf, maybe the last question.
You showed initially as motivation that you see swarms of different scales, like you're showing sheets. Now, when you derive the theory, essentially it's a mechanical theory. You show that it's applicable to ants or other small creatures. I wonder, would it be applicable also when you speak about larger creatures such as sheep or?
Which part of it? The alignment?
Yeah.
So there is actually a recent work with Perwani. He's a French. He has a group in Marseille, Bordeaux, that does this sort of behavior analysis with sheep. They look at sheep agents. They measure their interaction with one another. I mean, they want, by doing their measurements, they found out that sheep. Initially, they thought they have either two states, either grazing or running with their peers. But they did something more refined, and they realized that there is another intermediate state that they're looking at their peers. And from this, they were able to reproduce a lot of the complex behavior in sheep that are grazing, which is important. They also trained some sheep. You saw that too in was that the same conference? I can't remember. They also trained some sheep to sort of become the leaders, and then they wanted to reproduce these experiments. Then they learned that their sheep were eaten But yeah, but people do that. I mean, people do that. Let's go into another maybe this is sort of the last comment. There is a nice work from I think 2 years ago that shows that people also act a little bit like stochastic agents once we're in very dense swarms, and it shows why we see laning in dense regions of people going in different directions. And they show laning is actually a hydrodynamic stable solution for a bunch of people going in opposite directions. And it starts from stochastic agents, people.
Okay, let's thank the
Yeah.
speaker again.
Thank
And, Mohammed here during the day, so whoever has more questions to ask can catch him. So see you next week.
ויש לנו המון דיאטי, כשיש יחס של הרמז דיפוזיה עולה מעבר לתשע מסוים, החלקית הזאת עוברת
זה כאילו משמעותי.
וואלה.
אני נכנס עד 22 במרץ, כאילו שבוע אחרי שהסמסטר מתחיל.
לחודש.
חודש.
אתה גם חושב שאנליטית אפשר ללמוד מהטלפונים?
אנליטית?
לדעתי לא.
לא.
רגע.
אני פשוט, אני לא לקחתי אנליטית
שנה שעברה?
כן, לא לקחתי אותו.
לא,
לקחתי אותו השנה, והשעה הראשונה שאני הייתי התחופף עם השעה האחרונה של הזמן. וכאילו אני מתלבטת נורא אם לצאת כאילו מאחרי ההפסקה וללכת להישאר, ואז אני מתחילה את חצי שיעור של זמנים את כל השנים. שכבר הייתי להישאר על כל זמן, אני לא הולכת להפסקה שלנו.
אני לא יודע מה אלי שואל כאילו במבחנים, אבל אבי מאוד אוהב לשאול דברים מההרצאה.
נכון.
מההרצאה?
ממש אוהב לשאול.
כי
מההרצאה.
כאילו כי באופטיקה למדתי את החומר מההרצאות בעיקר. אני לא יודעת אם זה ככה גם באנליטיקה.
לדעתי, כאילו האנליטית, גם במועד א' וגם במועד ב' היה שאלות מההרצאה. יש לו בהרצאה כזה שהוא עושה פוטנציאל מרכזי, אחת חלקי 4 ריבוע, אז הוא אמר תעשו בדיוק אותו דבר רק לאחת חלקי 4 שלישית. תזכור מה שהוא עשה בהרצאה.
זה אנליטית? כן.
אוף, אני ממש מתלבטת מה.
לדעתי כתקצי לאנליטית. הוא שואל כאילו...
ולהשלים את השעה הזאת אחרי זה של...
לדעתי כן.
אחרי זה תיקונתי אחד למדתי רק מהתרגולים.
גם אני, אבל נראה לי
שמע, קניתי אליו, בשביל לא להתבטא.
לאן אתה עושים אותי בסמסטר?
איזה כיף.
לאן אתה עושים אותי בסמסטר?
לא,
יפה, ממש קדימה.
על המועדי ב'.
אני מכניקה סטטיסטית. אתה יודע שמה זה ניחמת אותי שאמרתי שיש מועד ג'?
כנראה, אילו זה אותם שעות אמרו תגיד, טוב.
כמה עולה קפה? 10 שקלים? 12? מתי זה עלה?
לא רוצה לבנות פשוט, צריך להכין לכם על הקפה.
אבל אין לי את האמצעים.
אמצעים.
אני אספיק ללכת את זה?
כן.
למרות שאני כעת באמצע ההקראה.
רגע, נראה לי מרצה שמתחיל כאילו לא, אין הקדמה, אין לאט לאט רגוע.
לי יש פשוט... לא, יש לי אוכל, אבל...
אין אצלה, מה אני קורא פה, כאילו...
לא קל.
לא נגעתי כבר לשפיים במה שאני עושה איתך.
החיים האלה, חפה.
איזה מוד.
את פה בבוקר ואת כזה.
היום לא הצלחתי,